Okay, vector field. Okay, and we got negative y over x squared plus y squared, x over x squared plus y squared. And then, so our general notation for these vector fields are going to be P and Q. P is going to be our normal conventional name for the x component of a vector field. Q, y component, and then when we get there, if it's R3 vector field, then it would be P, Q, and R. Each of those would be functions of x, y, and z. Okay, so this is our standard conventional notation, P and Q, for x and y component of a vector field. And so question is it conservative? How can we check? Is it conservative? How can we check? So there's kind of two ways we can check, right? One way we can check is we can just try to find the potential function, right? What's the other way we can check? Should we learn a new way to check? Yeah?
Take the second partial derivative of each.
Right. So we want to do P with so if this is a gradient field, this is the first partial with respect to x, right? And this is the first partial with respect to y. So what do? Take this with respect to y, and this with respect to x. So we need either the quotient rule or the product rule here, right? Either the quotient or product rule. So I think I do it by product rule. Yeah, so I use the product rule, and we're not gonna take the time to do the math and show that yes, indeed, if you do the math on these, if you do the product rule on that with respect to y, and the product rule on that with respect to x, and you do some algebra, you take some algebra, some fractions to work this out, you get y squared minus x squared over that denominator squared in both cases. Conclusion?
Yes, conservative.
All right, so conclusion would be that it's a conservative vector field because Clairaut's theorem holds that these were indeed partial derivatives of some potential function, okay? Which we didn't find, but we checked that it is. So here's that. I'm going to show you that vector field, and I'm going to show you two closed loops in that vector field. And so what can we say about the line integrals? What do you predict for these circulation integrals, right? So if we do a line integral around a closed loop, we call that a circulation integral, right? And so we got the path of the blue square and the path of the red circle. What do you predict for the values of those circulation integrals? Should be thinking 0 if we're in a conservative vector field. All closed loops have circulation 0, okay? So I'm going to just show you the math for the blue square because that's a lot of work to do. It's not hard work, but it's a lot of work. So this first one here is from 1 to 2, so I let just t be x, and we're going to do the integral from 1 to 2 of p times 1. This is my dr would be 1 comma 0, and then I get 0 for that. And then the next part of the journey here is this. I'm going to let t be y. I'm going to integrate from 0 to 1 because my y goes from 0 to 1. And this is what happens when you do f.dr, and I get 0.4636. Similarly, we go back and let t be x again, and I'm going to integrate from 2 to 1, and I get 0.3218. And then the last leg here, I'm going to let t be y, and integrate from 1 to 0, and I get negative 0.7854. And lo and behold, when I add up those four individual line integrals, I get 0, just like we thought, right? Okay, good. Okay, now I want you to do this one. So I'm going to do one loop, one counterclockwise loop around the unit circle in this vector field. And I want you to confirm that the circulation is indeed, what is it? Should be 0, right? So do the line integral, confirm that that is indeed 0. Check with each other as you go so you don't dig a bad hole for yourself. So what does it take? You're going to have to, so I call this C1, I think. How many people got that? People got that? Yeah? Some? Okay. And that's 0, right? Check. Right? No? What's wrong? What happened? Did we make a mistake? What is this? 2 pi. What's happening? What's going on? It's supposed to be 0, right? It was conservative. These are equal. We got a closed loop.
Guess not. 2 pi.
Oh, so it's even worse if you go around a second time. Is that what you're saying?
No, we parameterize in terms of theta, so 2 pi is the same as 0.
No, it should be, conservation of energy says that whatever positive contribution around here has to be canceled out by a negative contribution, so it's not equivalent to 0. This is 2 pi. This is a number, 6.28, whereas it should be 0. Okay? So, I'm going to hold you in suspense. Okay? So, something's up here, right? Something's up. Based on everything we've learned so far, there's something that's not jiving, right? Something doesn't jive. So we're going to put this on hold, and we're going to talk about some other stuff, and we're going to come back to it. Okay? Okay. Questions? All right. So we want to talk about something called. Okay. Green's theorem. So let's talk about something called Green's theorem. Here is Green's theorem. If you would, I don't want to take the time to have you write all that down. So if you want to write that all down, maybe you're looking at the video later, or just abbreviate it. But we want a simple curve. If you just mostly listen to make sure. Simple curve is a curve that never crosses itself, first of all, and a closed curve is a curve that makes a loop. Okay, like in our circulation integral. So we make sure it's simple, it doesn't cross, and it makes a loop, and it's going to create a region D. Okay, so if you have a simple closed curve, that creates a region inside. We want to call that D. And we want to orient that so that the region is on the left as we traverse. Meaning, see if I have a picture? I don't have a picture. So here's some C. It could have straight lines like our square. It could be a triangle. It could be an ellipse, could be a circle, anything that's simple and closed. And so the boundary is C, and then inside it creates a region D. And so we want to orient this, meaning there's a direction, right? It's either going to be clockwise or counterclockwise. Which one do we pick, counterclockwise or clockwise, so that the region is to our left? Just to say like we're walking this like a path. We want the region to be to our left. So it'd be clockwise or counterclockwise? Counterclockwise, okay? So positive orientation for this would be counterclockwise. Or in other words, if we walk it as a path, the inside is to our left. That'd be counterclockwise. And then we have all this stuff we're talking about is in some vector field, okay? F, P, Q. is a vector field. It's defined everywhere on C and D. Then here's Green's. So that's all the setup. This is what we need to have for Green's theorem to hold. Then we get this thing right here. Okay, what does it say? It says that if all this stuff is true, then the circulation integral on C is equal to the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y. So that makes a function of X and Y, right? That makes a function of X and Y. If you take the double integral of that function over D, that's the same as the circulation of the boundary C. So now this should kind of ring some bells here. When you say Q, partial of Q with respect to X and the partial of P with respect to Y, that should be familiar. What does that remind you of things we've done recently? Checking if it's conservative, right? And if it's conservative, what is true? These are equal, right? So if these are equal, then what function are we integrating? 0. And then, but that's if it's conservative, right? If we're in a conservative vector field, what about the circulation integral? 0. So very quickly we see that this holds in a conservative vector field because these would be equal in a conservative vector field, making that 0. And we know that all closed circulation integrals are 0 in a conservative vector field too. So we get 0 equals 0. So Green's theorem, it's kind of like in a conservative vector field, that's like a trivial case. It's like the uninteresting case because you get 0 for both sides. And it holds. It's perfectly legitimate. But it's like Green's theorem is much more interesting in a non-conservative vector field when you have non-zero integrals. Does it make sense? Okay. So how does this relate to the standard fundamental theorem equation? So here's the equation for the fundamental theorem of calculus. Actually, this Green's theorem is a kind of a variation. It is a fundamental theorem. So it has lots of parallels to this. So I want you to take a second to look at this and decide how is this parallel, in what different ways, what aspects is this parallel to our standard, our original fundamental theorem? All right, so how is this parallel to our original fundamental theorem? And one aspect of that is like which side, how do the sides match up? Do the left sides match up and do the right sides match up, or does it match up like a crisscross? Like, does this match up to this and this match up to this? That's one question you have to answer. And then beyond that, how are there other aspects that these are similar? So get a partner. Everyone's talking to somebody. Get a partner and try to figure out, first of all, how do the sides match up? And then what are some other qualities of this Green's theorem that are analogous to the fundamental theorem? Go. Everyone's talking to somebody. Okay, so let's first talk about which sides match up. So how many concluded the left matches with the left and the right matches with the right? And how many think it's crisscross? You're all abstaining? Okay, try again. It's okay. Who thinks the left matches with the left and the right matches with the right? The left sides match up and the right sides match up. Okay, and then the other, so that it's matching up across. So more matching up across. Okay? You're correct. All right? They match up across. Okay? So what do we say in the fundamental theorem? The left side, on the bottom one, that one over there, the integral from a to b of the rate, that's what? That's accumulating little bits of a quantity by using the rate of the quantity, right? It's accumulating up lots of little bits of the quantity. I think we talked about that when we did partial derivatives, right? M times dx, right? The rate of change times dx gives you a little change in y, and we accumulate all those little changes in y. So that's kind of like the double integral. It's like we're accumulating up something something to do with rate of change, right? So these are like rates of change, right? It's the partial with respect to x, partial with respect to y. So this is something of a rate of change. And we're going to accumulate all those up, what, on the interior of the path, in the inside, over d. And so that's kind of the same here. We're accumulating up all these little changes in the interior, right? Between a and b is like the interior of x values, right? And each of those, like we said, each of those little bits is calculated by rate times change of the independent variable. So this is kind of like your m dx, right? This is like your m dx, m dx. Okay, so the accumulation of many bits is calculated, each little bit calculated by rate times change of independent is equal to what? Equal to what in both cases then? What's that? Yeah, so it's like your overall change in accumulation, right? Your overall change in accumulation. So how do we see that? So that's, final minus initial. That's easy, right? It's like your final value of the quantity minus your initial value of the quantity. So it's the overall change. But how do we see that here? How is that seen by this line integral? How are those kind of analogous to one another? Yeah?
Is it because the value of line integral is the final minus initial?
Okay. So, yeah, it's not quite, right? Because we're still going to integrate around this loop. But what is it about these that are kind of the same? So yeah, so it's loosely like that, right? But they both pertain to what? So it's like associated with the boundary, right? So if in an interval of x, you look at the net change from the end to the finish, and that's like the boundary of your interval, right? And here, we're looking at kind of it's the overall net accumulation of what's inside around the boundary, right? Around the boundary. So the accumulation of many bits, right? Each calculated as rate times change in independent is equal to the net change of the quantity associated with the boundary. So that's how these are the same. And this is really true for all fundamental theorems, right? So we've seen two now. We saw the fundamental theorem of line integrals, which obviously fundamental theorem of line integrals is kind of almost the exact same as this, right? And now we're seeing it for more like a higher dimensional case. Like this is now in like a R2 dimension. Okay, but it has the same kind of pattern to it. Oops. So, any questions about that? So really important because we're going to see more fundamental theorems, and we're going to look at how those fit this same pattern. Yeah.
What are the little bits we're accumulating on the right there?
In the top equation?
Yeah.
We're about to do it. I'm just kind of show you. I'm not going to give you a proof of Green's theorem, but I'm going to kind of walk you through what's going on. So that should answer it. Other questions? Okay. So so here's the deal. We're going to look at here's our D and our C. Okay. And so what we're going to do is we're going to sum. The little bits are going to be the circulation around little elements. So this is like each one of these little squares in here is called is like a little delta C. It's like a little circulation inside. And we're going to sum all those up. And that's going to take us in two directions, okay? Two directions. We're going to do that in two different ways. And because it's really doing the same thing, they're equal. Okay, so the first way is easy. So the first way, jump the gun here. The first way we're going to sum up these little circulations inside is we're going to look at what happens to adjacent ones, right? So I'm going to sum up the circulation of one square and the one next to it, and what do you see is going to happen? So as I come on this edge here, I'm going this way. And then on this one, as I come on this edge, I'm going this way. So when I add those two together, what's going to happen? They're going to cancel out. You're going to have a positive line integral, and you have the negative here. So those are going to go away. And so then when we do that for all of them inside, we're going to add up all the little circulations of the delta C's. What's going to happen? Every shared side is going to go away. Do you see? Leaving what? Just the closed loop of C, right? Everything that doesn't have a shared side is going to be only the closed loop of C. So all shared sides of elements sum to 0, leaving only the sum around the boundary. Okay? So that's the easy way. That's the easy part of this. And that's the first way we're going to think about doing this. So again, we're going to think about adding up all these little circulation integrals in two ways. And the first is we're going to think about how when we do that, all the shared sides cancel out, leaving just the line integral around the boundary. Now the second way we're going to do that is we're going to actually do one of them, okay? So the second way is we're going to actually figure out what this little circulation line integral is, and this is a little trickier, but we'll just do our best. We won't take a lot of time on it. So here's a typical little circulation, delta C in here, and then we have, it's in a vector field, right? So there's some vector f, and that f is made up of a x component that we call, what do we call that? The x component? P, right? And then we have what the y component is called? Q. And that's a function, right? So at a particular little circulation that we're looking at, this rectangle that we're looking at, we have some associated vector in the vector field with that. And we'll call it f with components p and q. So the first thing we're going to look at is we're going to notice that the top two sides are parallel. And so they're both just matters of what? Dx, right? So we could do, like, if we made our t the x coordinate on both of these. So that's adding the line integrals from C1 and C3 together, because those are like apples and apples, right? So I'm going to add those two together. And what's going to happen there is basically, when I add these two together, it's looking at what? The change in P from down here to up here. And what is the difference between those? Well, that's just delta y, right? So I have the P at the bottom of this thing, and the P at the top of this thing is just delta y up from there. Okay, so I'm going to do my f.dr, but that's just going to really amount to P, and then I can combine them, and this is positive, but this is negative, right, because we're heading back the other way. So it's going to be P down here minus P up here, and then dx, because we're just talking about in the x direction. Okay, so that's like half of the little line integral. Like this is the half that involves those two legs of the line integral. Is it okay so far? Okay, so then what is that equivalent to? Well, what's really happening here is that when we take this minus this, it's really how much P is changing with respect to y, right? So it's really how much P changes for a little change in y. So that's like the partial of P with respect to y. And then here's my dx. So this thing in parentheses is the same. It doesn't include the delta y, but all this here is the same as what's in parentheses here. And so by adding these two sides of the line integral, it's really the same as what is P with respect to a change in y, like when y changes a little bit. How much change in P do we get? And since y going positive is this way, and we're looking at the change from going in the positive x direction to going in the negative x direction, it's negative, right? So it's like as we go up, it's really how much change do we have that way. So that's why there's a negative sign here. Okay. So if we do the same thing for the vertical sides of this little delta C loop, we get something equivalent, all right? But now it's positive because from here to here, it's how much change, what, in y, from here to here, it's heading down negative and then turning up positive here. So as you go as a dx, it's positive. So we're adding that plus that. And that is how much does the q component change with respect to a change in x. So really what this is all calculating is kind of like turning rate of change. Like we put all those four together, it's kind of like a rate of change, like curling rate of change. And so what we're going to do is we're going to take this one minus this one, and we're going to sum all those up. So when we sum up all these single integrals, we get a double integral. Okay, so then here's our, this is like our dA here, and like a little dA here. So we're accumulating all the changes in the p with respect to y, and also all the changes of q with respect to x. And by subtracting, it's like we're accumulating up all that curling change, or twisting rate of change. So so it's like summing up all the bits of rotational accumulation. And so that gives us this thing. Qx is how much we get from vertical, and Py is how much twisting we get from horizontal. And so then we're going to sum all those up over d, and we get that. And so since those are both the accumulation of these little circulation integrals inside, both looking at how all the shared sides cancel out, and then actually doing them one at a time and adding them all up, then we get those two are equal, and that's a kind of a short version of that's kind of a loose proof of Green's theorem. I'm happy to dive more into this in office hours if you're interested and you want to get more of the details of this. Happy to do that, but I want to give you at least a little justification for what's going on here. Any questions on that? Okay, so let's do examples. All right, so really this example is I want to verify Green's theorem for this scenario. Okay, so I want to verify Green's theorem for this scenario. The circulation integral, where here's our vector field, and C is a triangle traversed from 0, 0 to 2, 0, 2, 4, back to 0, 0. Okay, and so that should be an easy picture to draw. Draw up here. So we're going to go from 0, 0 to 2, 0 to 2, 4, and then back to 0, 0. Okay, so what does it mean to verify Green's theorem? Verify, what would that imply? How would we proceed here? What would that mean to verify Green's theorem? Yeah?
Find the same answer two different ways.
Find the same answer two different ways. Yeah, it would mean calculate both sides and show that they're equal. It would mean calculate both sides to show that they're equal. That's what verifying a theorem would be. So we've got to do the line integral, right? So over here, we're going to do the circulation, f dot dr. And over here, we're going to do, what will we do over here? So that's over C, the double integral of d, over d, of q x minus py dA. So we have all the tools to do this because we know how to do line integrals and we know how to do double integrals. So we just got to set those up for this particular example. Okay, so what does doing the line integral entail? How are we going to have to, how do we do this line integral? 3 parts, right? We're going to have it's like a C1, a C2, and a C3. So should we split up? How about you guys do C3, and I'll do C1 and C2. So just do C3. Sarah, how did you parameterize that C3? How did you parameterize?
I made x equal to t.
Okay.
And then y was equal to 2t.
She did T, 2T. Okay? Andrew, you give me the eyes. So there's a lot of ways to do it, but this is easy, right? Because it's from 2, 4 down to 0, 0, it's just the line y equals 2x. So this is a nice way to do it. Okay, so then you integrated, or then our dr is? What is it? 1, 2. Now, so if you started off with a different parameterization of the curve, you can go with what you did and just carry it out. You should get the same answer in the end. You should get the same answer. So don't change it. It's a nice check, okay? So if you did something to, like Andrew, what did you do? What did,
No, I was just checking your C2.
oh, okay, sorry. It was not about that. Okay. Do you agree with it?
Isn't it supposed to be, the x one is supposed to be 2?
Yes, 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 yes.
So we're supposed to be S.
8. And then that's not 0. Good, thank you. So what is it? 32? Okay, back to C3. So we got that, and then we're going to do integral from. Sarah, keep going, doing good.
Okay, so from 2 to 0.
2 to 0, right? Because we're heading down this way, right? Down from that point to that. So it's going to be 2 to 0 of,
I got 10t.
what is it?
10t.
Let's do it out here. So
Oh, t.
2t, comma, 4t, dot, 1, 2, and is that, you said that's 10t?
Okay, wait, I thought I did something wrong there.
No, it is 10t, that's right.
Oh, I know it is.
2 and 8, that's right. 10t from 2 to 0. 5t squared, negative 20. So f, that integral, circulation integral is 12. Because it's going to be the sum 0 plus 32 plus negative 20. Agree with that? Okay, what about this? So we're going to find qxpy as a function of x and y. We're going to do a double integral over d. We're all experts at double integrals. What is qx minus, okay, so any questions about the circulation on the boundary C? Are we good? All right, so qx minus py, what would that be? Noah.
Oh, on boundary X, that would be, sorry, that'd be 0.
Let's do it. What's q with respect to x?
With respect to X, that's Y with respect to X.
Uh-huh.
That's 0. Yeah.
No, here, this is our p and q. This is the vector field, right?
Oh, I'm in the wrong one. Sorry, it's 4.
4, okay.
Yeah. I had them switch.
And then?
Then that's 1.
Okay, over D. Okay, and how would we do that? How would we do this double integral over D? Gavin, how am I going to do this double integral? So I got a double integral 3dA. So I need limits of integration. Okay, Caitlin.
You do left to right, bottom to top.
Okay,
So from 0 to 2, or probably from bottom to
bottom to top first, I agree. Because we know this function is, what is this?
2x.
2x. Okay, so let's do bottom to top first.
So 0 to 2x.
0 to 2x,
And 0 to 2.
0 to 2. And that would be d dx. Okay, now before we do that, so yes, so if we were to work that out using antiderivatives, we would get 12. But what is it? So yes, so antiderivatives. So there's one way to do this, antiderivatives. I mean, you just evaluate the double integral. What's another way to conceive and solve this? Anyone see another way that we could do this? Eric?
Theory times 3.
So is this the same as 3 times the double integral over d dA? That's a constant. Can I pull it out in front? And what is this? It's the area of the triangle, right? Because our function is 1. So I can pull that 3 out, and now I'm left with the area of, this is the area of the triangle. Which is 1/2 base times. So we do 3 times 1/2 base is, height is, equals happy face, right? Happy face. Okay, so verifying Green's theorem means you got to do the line integral and you got to do the double integral and show that they're the same. In this particular case, when you do this double integral, you get to here, you could use antiderivatives to do the double integral, or you could recognize that this is just 3 times the area of the triangle. And those are both valid ways to say what the answer is. Okay, web work tonight.